So this is a lecture on the course name is Renewable Energy and Green Technology, and we are in unit number 3. And the topic for the day is Introduction to Solar Energy. So, as a prerequisite or recapitulations to today's lecture, we have already seen, and the prerequisite includes the energy sources, the various energy sources like the renewable energy source, the non-renewable energy source, the conventional sources, the non-conventional sources, and etc. And also the role of energy in agriculture. So, these are the two prerequisite or recapitulations that we must have to bring this lecture forward. So, some of the objectives of today's lecture will be about the major sources of energy, to what purpose that solar energy is used for, and what are the major challenges that we are facing in the world of solar energy. So, the whole lecture will be on solar energy. So now coming to the important topic of the day, that is what is solar energy. So solar energy, that is radiation from the sun, which is capable of producing heat, causing the chemical reactions, or generating the electricity. The amount of solar energy incident on Earth is vastly in excess of the world's current and anticipated energy requirements. So, if suitably harnessed, this highly diffused source has the potential to satisfy all our future needs. So, in the 21st century, solar energy is expected to become increasingly attractive as a renewable energy source, mainly because of its inexhaustible supply and its non-polluting character, in stark contrast to the finite fossil fuels like coal, petroleum, and natural gas. So it is the energy which is produced by the help of a sun. It's a clean fuel, it's a renewable source of energy harnessed by solar collection methods such as solar cells, and converted into usable energy such as electricity, as you can see in the image, which is the solar photovoltaic panel or the solar panel from which the solar energy can be harnessed. So, in coming to the sources of energy, we have broadly categorized into renewable and non-renewable sources. The non-renewables include those of fossil fuels and the nuclear fuels, which are inexhaustible, which are non-renewable in nature. And we also have renewable energy sources like the direct solar in the form of photovoltaic cell conversion. You have the biomass, you have the wind energy, you have tidal energy, and so on. So here you can see in the image, the slide is all about energy from the sun is abundant. So that is, the sun is an extremely powerful energy source, and sunlight is by far the largest source of energy received by our planet Earth. But its intensity at Earth's surface is actually quite low. This is mainly because of the enormous radial spreading of radiation from the distant sun. Relatively minor additional losses due to Earth's atmosphere and clouds, which absorb or scatter as much as 54% of incoming sunlight. The sunlight that reaches the ground will consist of nearly 50% visible light, 45% roughly infrared radiation, and some smaller amount of ultraviolet and other forms of electromagnetic radiation. So solar power systems installed in the areas defined by the dark disk could meet the world's current total energy demand. You can see in the image that there are around 7 to 8 dark spots or the dark disk, and that could meet the world's current total energy needs. So this slide will tell you the current United States energy demand. The US consumes nearly about 25% of the world's energy, but it has only 4.5% of its population. The solar cells would need to cover an area comparable to the size of Texas to meet the U.S. energy demand today. But if you project this on a broader scale, we see that to meet the projected U.S. demands, in 2050, the solar panels would need to cover an approximate a third of the area. You can see that in the image there are more solar panels which are going to come in the near future in the U.S. to meet its energy demands. So solar panel use today, so large companies like Google, Walmart, and Microsoft use solar energy to partially power some of their facilities. You can see in the image that solar panels on the Microsoft company building, which is using the power from the sun to power some of their facilities in their office premises. So next slide is all about an application of solar energy, that is in the field of solar cells. So what does this mean for solar cells? So solar cell or photovoltaic cell is an electrical device that converts the energy of light directly into electricity by the photovoltaic effect, which is a physical and also a chemical phenomenon. So it is a form of photoelectric cell defined as a device whose electrical characteristics such as current, voltage, or resistance vary when exposed to light. Individual solar cell devices are often the electrical building blocks of photovoltaic modules, known colloquially as solar panels. The common single junction silicon solar cells can produce a maximum open circuit voltage of approximately zero point 0.5 to zero point 0.6 volts. So solar cells are described as a being photovoltaic irrespective of whether the source is sunlight or an artificial light in that sense. In addition to producing energy, they can be used, they come very handy to be used as a photo detector in the case of infrared detectors, detecting light or other electromagnetic radiation near the visible range or measuring the light intensity. So in dye-sensitized solar cells, you can see that the graph is shown between the energy and the wavelength of incident radiation. You have the highest occupied molecular orbital level and the lowest unoccupied molecular orbital level, called as HOMO LUMO, and the band gap between both these energy levels is somewhere around 1.55 electron volt for a dye-sensitized solar cell. But in a single crystalline silicon solar cells, there are two states. One is called as the conduction band, and the other one is called as the valency band. It's where the valence electron sits, and conduction band is where the electrons cross over the band gap. After overcoming the band gap, they comes to the conduction band. So that's the excited states, and valence band is known as the ground state, and the band gap energy required to overcome the band gap is known as the band gap energy. So now coming to the working principle of a solar cell. So when light reaches the p-n junction diode, the light photons can easily enter in the junction through very thin p-type layer. And this light energy in the form of photons will supply sufficient energy to the junction to create a number of electron hole pairs. The incident light then will break the thermal equilibrium condition of the junction, and the free electrons in the depletion region will then quickly come to the n side of the junction, and similarly the holes in the depletion can quickly come to the p-type side of the junction. And once the newly created free electrons come to the n-type side, cannot further cross the junction because of the barrier potential of the junction. Similarly, the newly created holes once come to the p-type side cannot further cross the junction because of some potential barrier. So as the concentration of electrons becomes higher in one side, that is the n side, and the concentration of holes become more in another side, that is the p side, the p-n junction will behave like a small battery cell. So a voltage will be set up which is known as the photovoltage, and if we now connect a small load across the junction, there will be a tiny current flowing through it. So that's how the solar cell works. So the materials that will be used in making the solar cells will be should have a band gap close to 1.5 electron volt, and the common materials that are used is silicon, then gallium arsenic, then cadmium CdTe, then CuInSe2. So these are some of the materials: silicon, gallium arsenide, cadmium tellurium, and CuInSe2. These are the four materials that will be used in solar cell because their band gap is very close to 1.5 electron volt. And the criteria for the material selection is so they must have a band gap from 1.5 electron volt or plus or more than that. It must have a very high optical absorption, and the materials must have high electrical conductivity, and the raw material must be available in abundance, and the cost of the material must be low. So these were the few criteria that must be followed to select the materials for solar cell application. So light with energy greater than the band gap energy of silicon will be absorbed, and that energy will be given to an electron in the crystal lattice. The energy excites the electron. It is free to move. A positive hole is left in the electron's place. This separation of electrons and holes will create a voltage and a current known as photocurrent. So a silicon-based solar cell attributes, it is expensive in the sense that it is made in high vacuum at high heat, the high manufacturing costs. It need TLC, fragile, rigid, think, and long return on investment. It takes 4 years to produce energy savings equivalent to the cost of production. So some of the advantages of the solar cell is that no pollution associated with it. It must last for a longer time, and no maintenance cost is required here. But it also has some of the disadvantages, like it has high cost of installation, it has got a very low efficiency, and during the cloudy day the energy cannot be produced, and also at night we will not get solar energy. So these are some of the advantages and disadvantages of the silicon based solar cells. So how a dye sensitized solar cell works. So light with the high enough energy will excite the electrons in the dye molecules, and the excited electrons will then be infused into the semiconducting titanium oxide transported out of the cell. The positive holes will be left in the dye holes, and separation of excited electrons and holes that will create a voltage that is known as a photovoltage, and that's how you get a dye sensitized solar cell working, and that's how you get a voltage out of a solar cell. So this is the comparison between the dye sensitized solar cell and silicon based solar cells. In the dye sensitized, it is relatively inexpensive, but traditional it is expensive. Dye sensitized need very little TLC, but traditional needs TLC, and dye sensitized has short return on investment, but traditional has a long return on investment. So here in this slide, you can see the solar electric power plants. So uses of solar generation system. Number one, it may be used to charge batteries. Number two, it is used in light meters. Number three, it is used to power calculators and wrist watches. Number four, it can be used in spacecraft to provide electrical energy. So you can see in the image that it is using harness the solar power to generate electricity. So the main types include solar thermal energy, has mirrored surface that reflects the sunlight to heat up liquid to make steam to generate electricity, and also photovoltaic type where the photovoltaic cell that absorb direct sunlight also. So as we discussed earlier, so you can see the concentrated solar collector which is a parabolic type, and array of mirrored solar collectors at the FPL energy site in California. So these are some of the applications where the solar energy comes into picture. So direct heating of fluid, no conversion to electricity. The components include solar thermal collectors, a fluid system to move the heat, a reservoir to stock heat for later use. And some of the applications of this type of system is heat the water for home or pool. So example, system with water heated by solar collector and used to supplement hot water radiator. So in conclusion, we can say that though solar cell has some disadvantages associated with it, but the disadvantages are expected to overcome as the technology advances. Since the technology is advancing, the cost of solar plates as well as the installation cost will decrease down so that everybody can afford to install the system. So furthermore, the government also is laying much emphasis on the solar energy. So after some years, we may expect that every household and also every electrical system is powered by solar or the renewable energy sources. So these are some of the references from where the material can be read in detail, and also the references from where the images were taken are also properly cited. So these are some of the questions for you to answer. What are clean and renewable energy sources? What are current and projected global energy demands? How do newer nanotechnology influence solar cells work, and how do they differ from the traditional solar cells? So thank you for your time and attention.